Have you ever wished you could predict the future? I mean, really see what's going to happen? Well, in the world of chemistry, you kind of can. Chemists have this incredible toolkit that lets them see exactly where a chemical reaction is headed. So let's dive in and see how they do it.
The secret is to think of a chemical reaction like, well, like this dashboard. Over on one side, you've got your starting materials, we call those reactants, and on the other, you've got what you end up with, the products. And that needle in the middle, it's always trying to get to equilibrium. That's the perfect state of balance where everything just seems to stop. Our whole goal is to figure out what it takes to get that needle into the green zone.
So how do we do that? Well, we need our first tool. Think of it like a destination you plug into your GPS. In chemistry, our destination is a special number called the equilibrium constant, or just Kc. It tells us exactly what that final balance between products and reactants has to look like. It's our finish line.
And you know, the idea behind Kc is actually super simple. It's just a ratio. You take the concentration of the products and you divide it by the concentration of the reactants. That's it. So if you end up with a ton of products, that top number is big, right? Which means Kc is going to be large. But if you're left with mostly reactants, the bottom number is big and Kc will be tiny. It's a direct measurement of how the reaction ends up.
But you know, this constant has to play by a few very strict rules. First, it only describes the system when it's perfectly at equilibrium, not before. Second, it doesn't care at all how you start the reaction. That final ratio is always going to be the same. Third, it is completely locked to a specific temperature. You change the temp, you've changed the destination entirely. And finally, a cool little trick. If you decide to run the reaction in reverse, the new constant is just 1 divided by the original one.
Now here's where it gets really powerful. The actual size of Kc tells us how far the reaction's going to go. If Kc is super tiny, like less than 10 to the minus 3, the reaction basically doesn't happen. It's negligible. If Kc is huge, we're talking bigger than 10 to the third, the reaction goes almost all the way to completion. You're left with pretty much all products. And if it's somewhere in that appreciable zone in the middle, you're going to have a nice healthy mix of both reactants and products.
Okay, so this is great. We know our final destination, Clask. But what if we just started our reaction? Or what if we're only halfway there? How do we know which way the car needs to turn to actually get to our destination? We need some way to find our current coordinates on the map.
And that is where our second tool comes in. Meet the reaction quotient, or QC. This is our "you are here" marker on the map. It's a snapshot of the reaction state at any given moment in time, not just at the final destination.
This map really makes it all click, doesn't it? Kc is that fixed pin on the map. That's the equilibrium state we're trying to reach. It doesn't move. But Qc, that's our current position, that little arrow moving along the path. We can measure it at any time t during the whole journey.
So, let's put them side by side. At first glance, you might look at the formulas and think, wait a second, they look identical. And they do. But the absolute key difference here is all about timing. Kc uses the concentrations measured only when the reaction has reached equilibrium. But Qc, it uses concentrations from any moment we want to look. So think of Kc as the permanent destination, and Qc as just a quick photo we take along the way to see where we are.
All right, now we have both pieces of the puzzle. We have our destination, Kc, and we have our current location, Qc. And now the magic happens. By just comparing these two numbers, we can predict exactly which way the reaction needs to shift to reach that final balance. This is our diagnostic engine. It's super straightforward. If our snapshot, Qc, is smaller than our destination, Kc, well, that just means we don't have enough products yet. The reaction has to move forward to make more. Now, if Qc is larger than Kc, we've overshot the mark. We have too many products, and the reaction will actually shift in reverse to fix it. And if Qc happens to equal Kc, perfect, we're already there. We're at equilibrium and nothing's going to change.
Let's make this real. We can put this whole idea into practice with a really simple 4-step workflow. First, we set up the reaction. Then, we take a quick snapshot of the current concentrations. Third, we do a little bit of math to find Qc. And finally, we make our diagnosis by comparing it to Kc. Simple as that.
Okay, check out this case study. Our destination, Kc, is a pretty small number, 0.002. Now, at some random moment, we take a snapshot and we find that all 3 chemicals in our mix have the exact same concentration. So we plug those numbers into our Qc formula, products on top, reactants on the bottom. And this is important. See that 2 in front of the reactant in the equation? That becomes an exponent in our formula, so we have to square it. When we do the math, it gives us a Qc value of exactly 1.
So what's the diagnosis? Our current position, Qc, is 1.0. Our destination, Kc, is way down at 0.002. Since our QC is much, much larger than our target KC, it means the system has way too many products right now. So to find its happy place, its equilibrium, it has no choice but to shift in the reverse direction, turning some of those products back into reactants.
So we've covered a lot of ground, but it all comes together in one beautiful, elegant summary. You can think of this as your master map for predicting the future of pretty much any reversible reaction out there.
This flowchart just lays it all out. When you want to predict what a reaction is going to do, you just ask two simple questions. First, what's the reaction's extent? How far will it go? For that, you just look at the size of Kc. Is it tiny, in the middle, or huge? Second question, what's the reaction's direction? Which way is it moving right now? For that, you calculate Qc and compare it to Kc to see if it needs to shift left, right, or just stay put. That's the whole game right there.
So when you really stop and think about it, with just two little numbers, Kc and Qc, we've built an entire dashboard to understand and predict how these complex chemical systems behave. It's an incredibly powerful idea. And it really leaves you with a final thought. With a map this powerful, what other chemical futures could we possibly predict?